All right, guys, we are going to be starting astronomy today, and I just wanted to show you guys this really awesome solar system simulator, which is free and online, and you guys would, I think, really benefit from trying this out. So it's called solarsystemscope.com, and I'll put the link on the agenda for today. But astronomy can be pretty tricky when it comes to understanding the motions of the Earth and the sun and all the other planets in our solar system. So what we have to kind of look at are two words which are going to be really important, and I want you to understand the difference between them. This is showing you right now, not to scale, but it shows you currently where the planets are aligned relative to the sun. And you can see, obviously, we have the sun in the center and all the planets going around the outside. Now, what I'm going to do is I'm going to speed up time a little bit. So I'm going to press play here. Right now, it's currently stopped, and we can play it at actual speed, or we can just play it sped up a little bit. So right now, 26 minutes in real life is 1 second in the simulator. I can speed that up even more. Okay, so I'm just going to go a little bit faster, and I want you to notice one of the motions of our planet right here, Earth. This motion, as you guys probably already know, the spin of the Earth is known as rotation. Okay, so the Earth, not only is it tilted on its axis, you can kind of see there's a slight tilt to the thing, it's spinning around and it's rotating. And every day it rotates once around. So if you look for, here comes North America and South America. Okay, there it is right now. It's the 24th of May. And you're going to see it come back around again on the 25th of May. There it is. Okay, so every day, one rotation. Okay, 360 degrees in a circle, one rotation per day. And we have already talked about that. Revolution is the other word I want you to recognize. And by the way, all the planets, if you look at them, they're all actually spinning or rotating. They rotate at different rates. Now, I'm going to speed up Earth and all the other planets a little bit more, and you're going to notice that other word, which is called revolution. Okay, and remember, revolution is going all the way around the sun. Okay, and you can see all the planets are going around the sun, and it takes one complete year to go all the way around the sun, to revolve around the sun. So just note the difference. Notice how much it's spinning every day. 365 times it's going to spin around as it goes around this whole entire loop. Okay. Now, one thing I also want you to notice is look how fast the planets are going around the sun, the revolution of those planets around the sun. The closer they are to the sun, the faster they revolve around the sun. And so Mercury and Venus are actually making a faster path. They have a shorter year, if you want to call it that, to go all the way around, to revolve around. Now, if I speed this up even more, you can really see that. Look how fast Mercury goes around the sun. Look how fast Venus is going around the sun, and there's Earth. Even the asteroid belt is revolving around the sun. Okay, and there's Mars kind of lagging behind there. If I zoom out even more, you'll be able to see some of the other planets. There's Jupiter, taking a really long path around the sun. And here's Saturn over here, kind of coming into view. Okay, and Saturn is taking even longer. It's a little farther away, so it takes longer to go around. And there's Uranus. Okay, and here's Neptune way out here. Okay, and there's the Kuiper belt beyond that. So just remember, rotation, revolution. Rotation is spinning, and revolving is going around the sun. Okay, so just going a little bit further with this model, the rotation of the Earth is what makes everything seem to appear to move across the sky. So as we're looking at this model in this mode, you'll notice that the sun is pretty stationary relative to the Earth. It's the Earth that's spinning every day. So that rotation makes everything look like it's moving across the sky. And we can look at that a little bit further if we change our model to the night sky model. And we just want to make sure that we're located in the correct location, because it's all going to depend upon our latitude. It's going to depend upon our position. So I have my location set to 43 degrees north, 76 degrees west, which is approximately Syracuse. So I'm going to say OK. And now what I want to do is I want to set my time to the actual time currently, which is May 20th at 9:57 a.m., which is when I'm recording this. And I'm going to spin this around, and you'll be able to see the sun is up in the sky at the moment, and it continues to go higher into the sky as the morning goes on. Now, if I speed up, I'm going to reverse time just to show you guys exactly where the sun rose this morning. The sun was rising not due east, but slightly north of east, right around here. Okay, so I'm going to stop that. And now we're going to fast forward time. We're going to just watch the path of the sun going across the sky. I'm going to zoom out a little bit. And you'll notice as the sun climbs into the sky, we're getting further and further into the morning. And now it's about what time it is currently. And it's getting higher and higher and higher in the sky. And I'm going to pause it right around noon, which is right around now. Okay. And you'll notice that the sun is highest in the sky right around noon. And we are facing pretty much due south, okay? And so the sun is always in the southern sky in the northern hemisphere in New York, and it's going to be pretty much due south at noon. Now, as we continue to move this forward, you'll see that the sun is going to come back down again, and it's going to set a little bit to the north of west. And that's this time of year. So right around now, it's setting, and there it goes below the horizon right there. Okay, so you can see it's setting north of west. Okay, so now that you guys have seen the simulator, let's just go through some of the notes quickly. I'm just going to teach you part of this today. These notes will be online. So some of these presentations are done by other people. If you want to check them out, they're under the topics page of astronomy, which is our last unit. Just a couple of other words related to some objects in the sky that we're looking at. If we want to find exactly where something is in the sky, we use these two A words, azimuth and altitude. Azimuth is a direction in which we line ourselves up if we want to face north, south, east, west. Rather than giving us like a compass direction, we give it an angle. And so north would be exactly 0. And if we spin around perfectly around, like in my chair, which I just got, new spinny chair, if I spin around south, now I am facing 180 degrees away from 0, so that would be 180. So we can pick an angle in which we're facing. Okay. Altitude, which we already learned about earlier in the year, is the angle above the ground, angle above the horizon, how high in the sky. So we learned about that with Polaris. Zenith is the point directly above your head, and that would be 90 degrees, so straight up. Okay, so just know these words. That's how we find things in the sky. Now, as I just showed you in the simulator, the sun generally rises in the east and sets generally in the west. And it kind of depends upon where you are, and it depends upon the time of year, but it always rises in the east and sets in the west for everybody on Earth. And that's because the Earth is spinning from west to east. The sun reaches its highest angle around solar noon. Okay, now solar noon might not be perfectly noon, but that's when the sun gets to its highest point in the sky. It kind of depends upon where you are in the time zone as well, but it always reaches the highest angle at solar noon. Okay, now for us in New York State, the sun is always going to be in the south at solar noon, which we just saw that in the simulator. Okay, now you can look at the path of the sun by measuring shadows, and these are sundials, different types of sundials. This is actually a sundial that's on the Cornell campus, which I might talk about at some other point. Okay, and I'm going to maybe give you some type of activity with this. All right, now, big thing, guys. The path of the sun across the sky, it all depends upon how the Earth is spinning, but it also depends upon where you are in our orbit around the sun. It depends upon the time of year. Okay, and we're going to look at that in a second. It also depends upon your latitude. So where you are relative to the equator, okay, whether you're further north or further south, it's going to really change the sunrise and the sunset. Equinoxes. Equinoxes are 2 days of the year when the sun rises exactly east and sets exactly west. And I'm going to show you that right here. On the equinox, guys, the sun is out for exactly 12 hours, and the sun is below the horizon for exactly 12 hours. And so it's a day of equal night is what equinox means, okay? So 12 hours of daylight, 12 hours of night. Now, if you look at these 4 pictures here, this is a picture showing you where the sun rises directly east, okay, on March 21st. Here is June, so this is to the north of east, okay? And here is September, that's perfectly east again, which you saw. And here's December, a little bit to the south of east. So depending upon the time of year, the sun is going to rise in different locations. Now, big, important point here. The sun goes across the sky because the Earth is spinning. And so the complete path of the sun is really a circle because we're talking about a rotating body that is a sphere, okay? So it looks like it goes across the sky in a circle. The part that you see is above the horizon. That would be day, obviously. And the part that you don't see is below the horizon. That would be night. Now, the rate of movement is equal to 360 degrees divided by 24 hours in a day, which equals out to be 15 degrees per hour. So how fast does the sun go across the sky? 15 degrees every hour. Okay? The length of the day depends upon the time of year, and we're going to look at that here. So here is spring, okay? And in spring, as you can see, this person is facing, in this case, it looks like he's facing a little bit to the north, but let's say he's looking at the sun rising into the sky. The sun rises perfectly east, comes up to an angle of about 48 degrees above the horizon, an altitude of 48 degrees, and that's around New York State at 42 latitude. And then it comes back down again perfectly west. So rising perfectly east, setting perfectly west. The path here is exactly 12 hours long. That's March 21st. We call that the spring equinox or the vernal equinox. Okay, so I've set my simulator for March 21st. It is 7:20 a.m. and you'll notice that the sun is exactly in the east. So when it rises, it's due east. I'm going to fast forward time, and I want you to notice how it's going up into the sky. Each one of these lines on this picture is 10 degrees of altitude. So it's going to get up to an angle above the horizon right around south of about 48 or so. It's going to be right around there at noon. Okay. And I'll pause it right there at noon. And you can see the angle is about 48 degrees, 10, 20, 30, 40. That's 50. So it's around 48 degrees. And then it's going to come back down again. And you'll notice that it's going to set perfectly in the west. So that's the first day of spring. Here is summer. Now notice the path is a little bit different. The sun rises a little bit to the north of east and rises up to a much higher angle. In fact, that angle is around 71.5 degrees, the altitude above the horizon. So it's much higher in the sky. And then it comes back down and sets north of west, so around northwest. Okay, so this is the longest day of the year. It's around 15 hours of daylight and then comes back down again. Okay, so it's a lot longer day and a shorter night. Okay, so I've set my date to June 21st, the first day of summer, and you'll notice that the time is around 5:48 a.m. when the sun is rising. And notice that it's rising a little bit to the north of east. And as I fast forward time, I'd like you to notice how high the sun goes into the sky. It's going to be an angle of around 72 degrees. Let me slow this down a little bit. Around 72 degrees when it reaches its highest angle above the ground. And that's right around here at noon. Okay. And then it's going to come back down again, and it's going to set a little bit to the north of west as we forward into the afternoon. It's setting right around now. Okay, notice setting in the northwest. So that's the first day of summer. Now let's go to autumn. Okay, so September 21st or so. And you'll notice that it's back to the old path of spring. So it's rising perfectly east up to a 48-degree angle, back down perfectly west. 12-hour daylight. Okay? So equal day and equal night. Okay, so I've set my clock to September 21st at around 7 o'clock in the morning. The sun is rising perfectly in the east. As we go forward in time, the sun is going to rise up to an angle of about 48 degrees, just like it did in spring. And then it's going to come back down and it's going to set perfectly in the western sky right around there at around 18:46 p.m. Okay. And then finally, winter. winter has a very, very small path. You'll notice it's a very short day. Sun rises south of east, comes up to an angle of 24.5 degrees above the horizon, and then sets in the southwest. Okay, finally, I've set my clock to the first day of winter, December 21st, and we call that the winter solstice. It's 7:55 a.m., so it's rising a little bit later in the morning. Notice it's rising in the southeastern sky, and I want you to notice how low the path is. It's only going to get up to an angle of about 24 degrees above the horizon at solar noon right there, okay? So really, really low path across the sky, low angle of insolation, which makes it cold. And now, as I fast forward time, it's going to set in the southwest right around there at around 16:08 p.m., which, by the way, is only 4 o'clock in the afternoon. So a very, very short day on the first day of winter, okay? So these three, actually technically 4 paths of the sun are really important ones relative to our seasons. So, depending upon the time of year, the sun is going to rise in different places and be out for longer or shorter, depending upon the time of year as well. Now, one thing I want you to notice is that these 4 seasons, the difference of this angle above the ground at solar noon is 23.5 degrees. So, from here to where it was at the equinox is a difference of 23.5 degrees. Okay. And from here to here, from summer to the equinox, is again 23.5 degrees higher. What is that number all about? That number is actually the tilt of the Earth, which is interesting. Okay, so know those paths of the sun and use that simulator to kind of play around with that a little bit. This picture shows you the sun at different times of the year, its path across the sky in New York City. So you can actually see which path is winter, which path is spring and fall, and which path is summer. The longest path is summer, the longest day. Okay? So why is summer so warm and why is winter so cold? Has to do with the fact that, number one, the sun is out for longer during the summer, and the sun is going up to a higher angle. A steeper angle of insolation, or the sun's angle, is going to make it more intense sunlight, which is going to warm up the atmosphere. Okay. So important dates to remember. The summer solstice, the first day of summer, is June 21st. The winter solstice is December 21st. The spring and fall equinox, vernal and autumnal, are right around the 21st, 22nd, or somewhere in that range, depending upon the year, depending upon leap years and stuff. But you can see they're all exactly 3 months apart. All right, one last thing just to guys tell you about is the direction of a shadow. And this is a different simulator. I can put the link on the agenda for today. But I want you to notice the buildings and the shadows of those buildings relative to where the sun is. So here's the sun right here, okay? And I'll just highlight that a little bit better. Here's the sun. And you're going to watch the sun rise up that red line and then come back down again. This is today, so May 20th. And you'll notice as the sun goes across the sky, it's going to change the shadow on the ground. And I want you to notice where that shadow is located at different times of the day. So here it is, the shadow is getting shorter and shorter and shorter as the sun gets higher in the sky. Okay, and you can kind of see how that shadow is being made by the sun. And then exactly at noon, right there, you'll notice that this shadow is pointing exactly to the north because the sun is exactly in the south. Now, as time goes on into the afternoon, the shadows now start to point the other direction towards the east because the sun is going into the western sky. So the direction that the shadow is pointing is going to depend upon the time of the day. Also, the length of this shadow is going to depend upon the time of the year. So, I can change a couple of things. I'm going to change a few useful times. Number one, here is the useful time of exactly solar noon. All right, so you can see the shadow is pointing perfectly to the north. All right, and I want to change the date. Here is a useful date, summer solstice. Notice how small that shadow is. Why? Because the sun is more directly overhead, as you can kind of see in the model. Here is the date of the autumn equinox, the fall equinox. Notice the shadow is a little bit longer. I got to change my time to exactly solar noon again. There it is. And again, it's a little bit longer. Let's change our date to the winter solstice. I'd like you to notice how much longer this shadow is. Why? Because the sun is a lot lower in the sky on the winter solstice. And then we're going to change the date to the spring equinox. Again, still pointed to the north, but notice that it is a little bit longer than a month. Okay, so when do we have the shortest shadow? It's on the summer solstice, and it's pointing directly to the north at noon. Okay, so play around with the simulators, and hopefully this will help you become acquainted with the path of the sun across the sky.